Welcome back to Severe Weather, and here's lesson three. All right, the first thing that we're going to do in this video is review the parcel trace. So remember, what the parcel trace is helping us to know is what is a parcel, what are we going to expect it to do, and how is it going to compare to the sounding that we get with this QT log P. So just a review of what is shown here. This is this QT log P, and these two lines that are plotted that are green and red, that's what we got from our weather balloon that we sent out. Um, and over here, we have pressure, and you can see that the pressure lines are closer together at the bottom and further apart at the top because it's logarithmic pressure change. Pressure decreases logarithmically as we go up. That's why it's called log P. And then the skew T part is because the temperature lines are actually tilted. Um, so that's very important to make sure, like a line that goes straight up, if we had a line plotted that goes straight up, that would still be temperature decreasing with height. For it to be isothermal, which would mean it is constant with height, it would actually have to be tilted since our temperature lines are tilted, if that makes sense. But to draw what a parcel is going to do, we start at the surface temperature. So we start at the bottom of the red line because the red line is the temperature, the green line is the dew point. Um, so we start at the bottom of the red line. Oh, no, sorry. Then you start from the green line and go to where those two lines connect. And this is considered our LCL. So this is where that's lifting condensation level. It's where our parcel becomes saturated. So I should have said you go parallel to a dry adiabat. So you go parallel to one of the solid lines that curve from the bottom right to the top left. You go parallel to that and then connect it with the line going from the dew point. So now they're connected, and now we continue our line following the wet adiabat, which is the dashed line. So you just parallel it. So see this dashed line, the blue line is roughly parallel to it. And now that's our parcel trace. So it's actually pretty easy. But what's going to be important is identifying certain features of the skew2 log P. So the LCL we already talked about. It is right here. It is the place where condensation occurs. Now our parcel is saturated. And we're saying parcel because we're just wanting to know what will happen as we go up. We know what the environment is doing, but what will air do? And this is going to tell us a lot of things. We're going to get into this soon. So the LCL is right here. Um, it's where you draw up from the dew point line. You draw up following the saturation mixing ratio line, which is the dashed line going from the bottom left to the top right. You follow that from the green, and then you follow the saturation, or you follow the dry adiabat um, from the red line, and where that top of that triangle is, that's the LCL. The LFC is going to be right here. It's where the parcel becomes warmer than the environment. See, right now it's cooler than the environment, but once it crosses over, it's warmer. That's the LFC. Yeah, LFC. I don't know why it says LCF. I feel like I did this one time before. Hang on a second. Okay, that's better. I think I sometimes say LCF on accident because least common factor, but it's LFC, which stands for level of free convection. And why it's called that, it's where the parcel can rise on its own. Below this, it's not able to rise on its own. And we'll talk about that um, in a second. But once it gets to here now, because it's warm, doesn't that make sense? Because it's warmer than its environment, it can rise now. on its own. The EL is equilibrium level, and it's the level where the parcel becomes cooler than environment. So now it crosses over again, and that's the top of our thunderstorms. And then there's an area that's created between those, between the LFC and the EL, which is called CAPE, which is convective available potential energy. We're going to talk a lot more about this in the next video, um, how it's calculated and what all it can tell us. Um, but the important thing is just because we have CAPE doesn't mean that we're going to have thunderstorms. And like I said, we're going to talk more about that in the next video. Then there's an area down here too between this start and the LFC, which is called SIN, which is convective inhibition. It's the energy that's required to lift the parcel to the LFC. So remember, I said the parcel down here, it isn't able to rise on its own yet because it's cooler than the environment. Um, but still, there is energy, sin, that is able to help it rise to the LFC. And once it gets to the LFC, then it can rise on its own because it's warmer than the environment. Now, the two other things, we have the CCL, which you find the CCL by starting where you did um, down here at the green bottom of the green line, bottom of the dew point, and you just draw all the way up to the CC, all the way up to where you get to the red, and where that is the CCL, which is convective condensation level. It's the height that the parcel would be at if it was heated from below solely adiabatically. And then convective temperature, you go to the CCL and then you draw straight down to the temperatures down here. And we see that the convective temperature is 37 degrees Celsius. It's the temperature needed for clouds to form by solar heating. Now we're going to review stability a little bit. Sorry, I have this winter hat on and I'm just going to take it off because I don't know. Um, so review of stability. So we talked about this a lot in the last video, but we need to know by looking at these environmental temperature or environmental lapse rates to know if it's a situation that's stable, unstable, or conditionally un unstable, instability, sorry. Um, so we're going to go through these A through G. Now, in order to determine whether it's going to be absolute stability, absolute instability, or conditional instability, we need to compare these red lines to these solid lines and dashed lines that are going from the top left to the bottom right. The solid lines going from the top left to the bottom right, that is our dry adiabatic lapse rate. And the dashed lines is the wet adiabatic lapse rate. And remember the sayings that I have. If the order, and we rate them in order of steepness, they're all negative slopes. Why? Because um, their rates, and the rates are negative slopes, negative rates because temperature decreases with height. So we're rating their steepnesses. Um, this and so if the order is DWE, dang what? Exit. It's boring weather. It's absolutely stability, absolute stability. And then if the order is EDW, then excellent damn weather. It's what we want if we want severe weather. Conditional instability is if the order is DEW. Now, just to tell you, it can never be WED because, as we talked about in the last video, it's impossible for the wet adiabatic lapse rate to be greater than the dry adiabatic lapse rate. But let's see. Let's start with A. The order for A is EDW because CA is steeper. Well, this is where it gets kind of confusing. You might think like it looks like a sh smaller slope, but we're really talking about which one is more to the left. That's probably a better way to say it. So A is going more to the left than these lines, the solid and dashed lines. It's more to the left. You can kind of think about it like a speedometer, like we're closer to slower speed. And with a slower speed, we would drive slower when there's severe weather. It's more to the left. Um, so it is unstable because of that. It's tilted more to the left. So that means it's a greater rate. And we actually call it super adiabatic because it's very much to the left. Now at B, it's not exactly on a solid line, but it is parallel to the solid line. So it's actually equivalent. That can happen. So we have D equals E, and then they're both greater than the wet adiabatic lapse rate. This is still conditional instability, but we are going to have a neutral atmosphere if we're at a part where we're using the dry adiabatic lapse rate, but we're unstable for the WALR. Because remember, if the environmental lapse rate is greater than a different rate, it's unstable. Now for C, the order is, you can see it is greater slope than the dashed line, but not greater than the solid line. So it's in between them. So that's the situation where I say, dude, see down here, I don't know. It depends on the situation. So it's conditional instability once again. We have stable if we're talking about this rate, unstable if we're talking about this rate. And I say talking about, it's really what's happening for the parcel trace. Because remember, once we get to the LCL, we switch which rate we use. So it's conditional instability with respect to if we're using one rate or the other, and that depends on if we've reached condensation or not. D is a situation where now it's equal to the wet adiabatic lapse rate, but still smaller than the dry adiabatic lapse rate. You can see it is parallel to the dashed line, but not as steep as the solid line. So once again, conditional instability. If we're talking about dry adiabatic lapse rate, it's stable. If we're using the wet adiabatic lapse rate, it's neutral. Now E is not as steep or not as to the left as the dash line or solid line. So that's the order DWE. Dang, what exit? I'm not interested. Because it's stable atmosphere. Now, F and G are also going to be stable because they are two um, less steep, less to the left of the other lapse rates. But F and G are special situations. F is exactly on the temperature line, and because it's exactly on it, it's called isothermal. Iso means the same, thermal is relating to temperature. It's isothermal if it's directly on that line. And then G is like so to the right that it's still stable, of course, but we're actually in an inversion because temperature is increasing with height. So if it's to the right of these isotherms, which are these lines right here, temperature lines, if it's to the right of that, like more to the right of it, it's an inversion because the temperature is actually increasing with height. So every letter A through F, temperature is decreasing with height because it's to the left of the isotherms, but G is so far to the right that it's actually an inversion. So I know that can be a little bit confusing. It kind of is, once you get the hang of it, though, it makes sense. So now we're going to talk about how and why the environmental lapse rate can change. We're going to talk about four different ways. The first is diabatic heating and cooling. Um, so this is just talking about our everyday temperature changes. So one way that the environmental lapse rate is going to change is just by the fact that temperature changes um, due to the processes of, the sun going up and down. Um, Increased radiation absorption during the day. We have heat loss during the night. Daytime absorption of heat heats parcels of air and they end up warmer than the environment and rise. So we have the sun's radiation coming down here and the planetary boundary layer that we know, we have absorption of heat. and parcels of air are able to rise by that way. And as the parcels rise, they end up warming the environment as well. Assumption violated because we remember we talked about in a previous video, we assume that they don't mix together, the parcels and the environment, but in reality they do. And so because of this absorption, the environmental lapse rate is able to change. Also, environmental shear is a factor. If we have a sheared environment, it's an environment where the wind direction and speed changes with height. So oftentimes with this skew-T log P data, we also see wind data, and it's common for winds to be southerly shifting to westerly as we go up. That's a sheared environment. A non-sheared environment is where there would be constant wind direction and speed, but more often than not, we have a sheared environment. And we can have shearing advection, which is thermal structure transported unevenly to a new location. So we have advection, which is horizontal heat transfer. We have uneven transfer of heat, and that unevenness can change the environmental lapse rate. Third thing, I kind of already mentioned a little bit, but it's advection, which is horizontal heat transfer. Um, these factors and with cold air advection and warm air advection can change the environmental lapse rate. So aloft, if we have cold air advection, there's destabilization of the atmosphere. Um, and if we have warm air advection below, destabilization, and we have situations reverse that are where there's stabilization. But if we have situations with destabilization, like warm air advection at the surface or cold air advection aloft, that can change the environmental lapse rate. Lastly, convection, which is vertical heat transfer, it is created through thermal currents, and as parcels are carried upwards, once again, they're going to mix with the environment, causing a stable layer to possibly end up neutral or unstable. Mixing can weaken an inversion, so that's important to note. And then PBL, we already talked about this. It's the layer that's influenced by Earth's surface, and where the inversion is the top of the PBL. Well, that's going to be it for this video. Thanks for watching.